Thank you for watching this short video series on pool chemistry. We're going to be describing some of the basic chemistry that takes place. So perhaps as you maintain your pool, it will be less arbitrary and more meaningful if you understand the chemistry behind what's going on. So there's a lot of measurements that we could discuss, but we'll be discussing 4 of them: pH, total alkalinity, calcium hardness, and chlorine. In this first video, we'll be discussing pH. Now the pH range for your pool should be between 7.2 and 7.8. Ideally, it should be around 7.4. pH is a measure of how acidic or how basic your pool is. A pH of less than 7 indicates acidic conditions, and a pH of greater than 7 indicates basic conditions. Now, what is pH? Well, pH is a measure of the hydrogen ion concentration. Now, hydrogen ion concentration is usually expressed in molarity. That's what these brackets mean. They mean concentration. Now, if one were to take the negative log of the molarity of hydrogen ion, that would give the pH. So pH is nothing more than a more convenient way of expressing how many of these hydrogen ions are present in the water. The pH of human blood is between 7.35 and 7.45, and the pH of tears is 7.4. So it's not coincidental that these numbers are essentially the same number here. However, the ideal value of 7.4 is not solely derived on these parameters here. There's other considerations as well. If the pH is not balanced, that is, if it's too high or too low, we're going to see some problems that develop. So if the pH is too low, the water becomes acidic and corrosive. We'll see damage to vinyl liners that causes staining. So for here, for example, you can see these screws are beginning to dissolve from the metal, and we're getting staining on the liner. So some of the metals on the surface begin to dissolve if the pool is too acidic, like chromium, for example. When that reacts with acid, you'll see that the chromium is now dissolved where before it was solid. So that's why you might get like pitting or corrosion on some of the surfaces. Additionally, copper ion is surprisingly the cause of green hair from swimming. It's not the chlorine. It's a little known fact. Most people think that chlorine causes the green hair, but it's not. It's caused from copper ions that I believe then when shampooed out actually don't come out, but rather precipitate into the hair as copper hydroxide and other copper salts. So once again, the green hair not caused from chlorine. So a low pH also dissolves grout in concrete. We know that grout, the material that's in between the tiles and the concrete, is made from Portland cement, and Portland cement has calcium sulfate in it. So calcium sulfate is what we find in between these tiles here. And if that dissolves out, well, we're left with calcium ion and sulfate ion. So how does that happen from a low pH? Well, we mentioned earlier that low pH means we have an excess, or we have a lot, of these hydrogen ions present. So it turns out that sulfate establishes an equilibrium with hydrogen ion to make sulfurous acid. So if there's a lot of hydrogen ion present, Le Chatelier's principle tells us that this reaction will shift to the right. Consequently, this equilibrium here will also shift to the right. So the calcium sulfate will shift and turn into more dissolved calcium ion and more sulfate. So sort of an interesting chemical description of what's taking place when this grout dissolves. So once again, that's the presence of the hydrogen ion shifts the reaction to the right, causing this to shift to the right and consequently dissolve. Now if the pH is too high, we get something called lime scale. Here you can see lime scale here right at the surface. Here we have significant lime scale buildup, and you can imagine that the water flow here would be severely restricted. So some of this pool chemistry that we're studying, it's not only pool chemistry, it's really water chemistry, and that has significant industrial and municipal considerations too. So calcium combines with carbonate to make lime scale. So this stuff here is, once again, lime scale. So here's an interesting reaction worth exploring. When CO2 dissolves in water, it produces carbonic acid. That carbonic acid then readily decomposes into hydrogen ion and bicarbonate ion. That bicarbonate ion can also further decompose to an additional hydrogen ion and a carbonate ion. So the question is, which one of these predominates in our pool? Well, this graph will help us out. This graph tells us which one of these will be most abundant and at what pH. So this dark line here, that's the concentration of carbonic acid. This dashed line, well, that's the concentration of carbonate. You can see that ends about pH 7, whereas the carbonic acid curve ends at about pH 9. And then lastly, we have the dotted bicarbonate line right here. So at a pH of 7.4, we go up until we hit the carbonic acid line. We go over, and it looks like there's a small fraction of carbonic acid at pH 7.4. Also, if we go up and over until we hit the bicarbonate ion line, you can see there's a large fraction of bicarbonate ion. So in a properly balanced pool, when the pH is 7.4, you can see we'll have mostly bicarbonate ion and some carbonic acid. Now, interestingly, look what happens to the carbonate concentration as pH increases. So at about 7.4, you can see there really is no significant amount of carbonate present. However, around pH 8 and pH 9, we begin to see that the concentration of carbonate climbs. And you know that once we have carbonate present, that carbonate will combine with calcium ion, which we'll see in a subsequent video is already present in the water. Well, that will make a lime scale. So once again, as pH increases, we increase the amount of carbonate, and the carbonate reacts with the calcium ion that's already in the pool, and that scales out as lime. As a side note, warm water situations are more susceptible to scaling. So this would be hot tub, and then when the pump is on, we would see that warm water cascades over the tile here. So here's a reaction we just saw. Calcium ion plus carbonate makes limestone. And this was dissolved CO2 and all of the species that it generates. So both of these reactions we saw. Noticed I've made bicarbonate and calcium ion to be highlighted red. It turns out that the two of these also have an equilibrium. Now we're not going to study this here too much, but take a look at the products. One of the products in the equilibrium reaction between these two is dissolved carbon dioxide, or aqueous carbon dioxide. And you probably remember from chemistry class that temperature and the amount of dissolved gas is inversely proportional. Meaning as we increase the temperature of the pool or hot tub, it can hold less and less dissolved gas. So as the temperature of the pool rises, the amount of CO2 that can be held in the solution decreases. So the CO2 that was or is aqueous now gases off and makes gaseous carbon dioxide. So what we've seen is we've reduced the amount of CO2 aqueous, and Le Chatelier would predict that the reaction would shift to the right to make up for that stress of losing CO2. So if this reaction shifts to the right, it will generate more carbonate ion, and then that carbonate ion will combine with the calcium that's present, and it will make limestone or limescale. And lastly, adjusting the pH. To decrease the pH, add HCl, or hydrochloric acid. In the stores, you'll see it marketed as muriatic acid. To increase the pH, add sodium carbonate, or soda ash. Sort of a interesting chemistry tidbit. If you were to think about sodium and carbonate and where they might, like, quote, come from, we would see that sodium, we could think about it as coming from a strong base, whereas the carbonate, we could think about that as coming from a weak acid. So it's almost like there's a tug of war. Sodium comes from a strong base, and carbonate comes from a weak acid. So who wins between a strong base and a weak acid? Well, the strong base wins out. So if we dissolve sodium carbonate in solution, it will produce a basic solution, thus increasing the pH.